Tonight, we're going to explore the oldest question we have ever asked of the night sky, and a small, silent object that may be holding part of the answer. It is sitting on Mars right now, not in a museum, not in a laboratory, not in anyone's hands. It is resting in the open, in the rust-colored sand of a place called Jezero Crater, in a thin and freezing wind made almost entirely of carbon dioxide. It is a titanium tube about the size of a piece of chalk, sealed at both ends. Its name is Sapphire Canyon, and inside it, locked in a little column of Martian rock, is the most careful, most hopeful, and most unproven secret in modern space science. Nobody is there to watch over it. The rover that drilled it has moved on across the crater floor, its tracks already softening under the drifting dust. The tube simply waits, in temperatures far below anything we would call cold, under a pale butterscotch sky, while the seasons on Mars come and go without a sound. It was drilled in July of 2024 by a NASA rover called Perseverance from a rock the mission named Cheyava Falls. That rock is ancient. It formed in the bed of what was once flowing water, back when this barren crater held a real lake, in an era so distant that the number almost stops meaning anything. And when the rover's instruments looked closely at the stone, they found something that made the scientists back on the Earth go very quiet and very careful all at once. They found tiny markings in the rock, pale spots ringed with darker edges that the team began calling leopard spots, because that is exactly what they look like. And inside those rings, two minerals had formed together. One is an iron phosphate called vivianite. The other is an iron sulfide called greigite. On Earth, both can be made by living things. Certain microbes, going about the slow chemistry of their lives in mud and sediment, leave behind vivianite and greigite as a kind of signature. So to find them sitting together in the bed of an ancient Martian lake is the sort of thing that makes a careful scientist lean in and hold their breath. But here is where we slow down, because this is a story that rewards patience rather than excitement. Those same minerals can also form without any life at all. Water and rock, given enough time and the right chemistry, can produce vivianite and greigite through reactions that have nothing to do with biology. The spots in Cheyava Falls might be the faint fingerprint of something that once lived, or they might be the ordinary handiwork of water moving through stone over unimaginable spans of time. From where we stand right now, we cannot tell the difference. And so the people who study this rock have chosen their words with real care. When their findings were published in the journal Nature in September of 2025, they did not say that life had been found on Mars. They used a quieter phrase. They called it a potential biosignature, a possible sign, the best candidate the mission has turned up so far, and nothing more than that. It is a door left gently ajar, not a door thrown open. There is one more reason to settle into the long view here. That little tube, Sapphire Canyon, is not coming home anytime soon. The plan to bring these sealed samples back to Earth, where they could finally be studied with every instrument we own, is genuinely uncertain. The mission architecture is under review, the budgets are being worked out, and the honest answer is that the rock may not reach us until the late 2030s, and possibly later. So the secret stays sealed. It sits in the Martian wind, patient, while we wait years just to ask it the next question. There is something almost tender about that. A chalk-sized cylinder, alone on another world, holding a clue we are not yet able to read. It asks nothing of us except patience. And it is a good place to begin, because Mars turns out to be the nearest doorway into a much larger and much quieter story. For a long time, when we have thought about the question of life beyond Earth, we have imagined only two possible answers. Either the universe is crowded, full of company we simply have not met yet, with signals we have not yet caught, and neighbors hidden just beyond our reach, or the universe is empty, cold, and silent, and we are alone in it. Two doors, one bright with company, one dark with solitude, and we have spent most of a century arguing about which one we are standing in front of. But the more closely we look, with sharper telescopes and steadier instruments and rovers reaching into the rock of other worlds, the more a third possibility comes into view. Not crowded, not empty. Something gentler and stranger than either. A universe full of worlds, where the conditions for life once arrived, held for a while, and then quietly slipped away. Worlds where the light, in a sense, was once on and is now off, with no one left in the room. That is the third door, and the little tube on Mars, sealed and waiting in the cold, is the first hint of what lies behind it. So this is not going to be a frightening story, even though it touches on endings. It is going to be a slow walk through a handful of finished worlds, our own quiet neighbors among them, to understand a single gentle idea. That being a world where life is possible is not a permanent condition. It is a season. It opens, it holds for a while, and it closes. And these seasons rarely line up with one another across the vastness of time. For now, there is nothing you need to do but rest. Let your shoulders drop. Let your breathing slow. You do not have to remember any of these names or hold on to any of these numbers. They will simply drift past you like the dust on the floor of Jezero crater, settling softly, while the voice carries you out past the thin Martian wind and into the wider dark, where the other quiet worlds are waiting. Take a slow breath. We have a long and peaceful way to travel tonight, and it begins with that single sealed tube, sitting alone in the sand of another world, keeping its secret a little while longer. If Mars has kept its secret quietly for billions of years, then the natural thing to do is to look further out. Past the orbit of Mars, past the cold giants and the icy edge of our own solar system, out into the wider field of stars. Because if one small world close to home can finish its season and fall silent, the question becomes simple and enormous at the same time. How many others have done the same? For most of human history, we had no way to even begin answering that. We could see the stars, but we could not see whether anything circled them. A star is so brilliant, and a planet beside it so faint, that finding one was like trying to spot a single moth fluttering beside a distant lighthouse. For thousands of years, the planets beyond our sun were purely a matter of imagination. That changed slowly, and then all at once. The first confirmed planets around a sun-like star arrived in the 1990s, and at first they came in ones and twos, each one a small triumph. Then came the survey telescopes, instruments like NASA's Kepler and later TESS, designed to stare at thousands of stars at a time and watch for the tiny, regular dimming that happens when a planet passes in front of its star. And the numbers began to climb, slowly at first, then into a flood. By the 17th of September 2025, the official tally kept by NASA's Exoplanet Archive crossed a threshold that would have seemed like science fiction a generation earlier. 6,000 confirmed planets beyond our own sun. 6,000 worlds, each one verified, each one orbiting a star somewhere in our corner of the galaxy. And that number has not stopped rising. There are thousands more candidates waiting in line, and the confirmed count keeps ticking upward month by month. Sit with that figure for a moment, because it is worth feeling rather than just hearing. 6,000 worlds, and counting. and these are only the ones close enough and aligned just right for our instruments to catch. The honest estimate drawn from these surveys is that planets are not rare at all. Most stars seem to carry at least one, which means the true number of worlds in our galaxy alone is not in the thousands or the millions. It is in the hundreds of billions. You would think, with numbers like that, the sky should be loud with company. And yet, when we listen, we hear nothing. No signals, no clear sign of anyone. Just the patient hiss of the cosmos and the light of stars that have been traveling toward us for a very long time. Now, you will often hear a particular phrase attached to the most exciting of these discoveries. A planet, the headlines say, has been found in the habitable zone, and it is one of the loveliest and most misunderstood ideas in all of this. So let us hold it gently and look at what it really means. The habitable zone is not a promise. It is not a description of a place that is green or wet or breathing. It is simply a band of space around a star, a kind of orbital slot, where the temperature would allow liquid water to exist on a surface if everything else happened to line up. Not too close, where water would boil away. Not too far, where it would freeze solid. A comfortable middle distance, sometimes called the Goldilocks band, where the math says water could remain liquid. But notice everything that little phrase quietly leaves out. Being in the habitable zone does not mean a planet has water. It does not mean it has an atmosphere to hold that water in place, or a magnetic field to shield it, or a stable climate, or a solid surface at all. It only means that one single condition, the temperature for liquid water, is not ruled out. The habitable zone is not a home. It is an address where a home could, in principle, be built. Whether anything was ever built there is a completely separate question. So when we say there may be tens of billions of planets sitting in the habitable zones of their stars across the Milky Way, what we are really saying is gentler and stranger than it first sounds. There are tens of billions of orbital slots out there where the conditions for liquid water are not impossible. Not tens of billions of living worlds. Tens of billions of slots where we simply cannot rule it out from here. And still, from all of those slots, that silence. This is the puzzle that has shaped a great deal of modern thinking about life in the universe. If planets are everywhere, and habitable zone planets are common, and the galaxy has been turning for more than 13 billion years, where is everyone? For a long time, people assumed the silence could only mean one of two things. Either the company is out there and we simply have not found it yet, or there was never any company to find, and we are profoundly, completely alone. But there is that third possibility we touched on, sitting quietly between the two. And it is best understood through a single image, one we will carry with us through the rest of the night. Imagine a great old library, the kind with high ceilings and long rows of shelves that fade off into the dark. It is evening now, and the library has closed for the night. The lights have been switched off, one bank at a time, and the rooms have gone quiet. But the books are all still there. Every shelf is full. Every story is intact. Every page still holding its words exactly where the author left them. Nothing has been lost. There is simply no one walking the aisles tonight, no one pulling a volume down, no one turning the pages. The library is not empty. It is full. It is just quiet and dark and resting. That is the third door. The galaxy may not be crowded with conversation we are missing, and it may not be a barren emptiness where nothing ever stirred. It may instead be something closer to that library, full of worlds whose stories already happened, or have not yet begun, or are unfolding right now in rooms too far away, and too long ago for their light to have reached us. The conditions for life arrived on world after world, held for a season, and then the lights went down for the evening, and the books were left resting on the shelves. It is a far more peaceful picture than either of the old two. Not the loneliness of an empty cosmos, and not the noise of a crowded one. Just a vast, dim archive of finished and unfinished stories, each one complete in its own way, waiting on the shelf in the quiet. And the beautiful, difficult part is that from where we sit, in our single lit room, we cannot easily tell which shelves hold stories that ended long ago, and which hold stories still waiting to begin. We see the building, we can count the rooms. We are only beginning to learn how to read the spines. So before we walk those darkened aisles, there is one more thing we need to understand, and it is not really about space at all. It is about time, because the real reason the library is so quiet may have less to do with how many books there are, and far more to do with when each of them was written. Here is what changes everything, and it has nothing to do with distance. Picture the night sky again, that whole field of stars, and the hundreds of billions of worlds we now believe hang among them. We tend to imagine all of it as a single photograph. One picture taken now of everything that is out there right now. But the universe does not work that way. The light from those stars left them at wildly different moments, some recently, some before there were oceans on Earth. What we call the sky is not a snapshot of the present at all. It is a layering of many different pasts. And once you understand that, the silence starts to look less like an absence and more like a problem of timing. The reason the great old library feels so quiet may not be that the shelves are empty. It may be that the readers came and went at different hours, and we happened to walk in during a lull. To see why that matters so much, it helps to take the whole story of life on Earth and shrink it down to something we can hold in a single thought. So imagine compressing Earth's entire history, all 4.5 billion years of it, into one calendar year. The planet forms in the first cold minutes of January the 1st. For a long time, almost nothing seems to happen. The earliest, simplest life appears sometime in the late winter or early spring, just microbes in the water. And then for month after month, that is all there is. Single cells, drifting and dividing, through a spring and a summer that last for billions of real years. Complex, many-celled life does not show up until the last few weeks of the year, deep in the autumn. The dinosaurs come and go in the final days of December, and everything we would recognize as human history, every city ever built, every language ever spoken, every star ever named, fits into the last 90 seconds before midnight on the 31st of December. 90 seconds out of an entire year. That is the size of the window we are living inside. Now hold that image and place beside it the silence we hear when we listen to the sky. The trouble is not just that our moment is brief. The trouble is that everyone else's moment would be brief too. If another world somewhere out there ran its own version of this story, it would have its own calendar, with its own long winter of simple life, and its own fleeting 90 seconds at the end. And there is no reason to expect that their 90 seconds and our 90 seconds would fall on the same night. This is the heart of it. For two worlds to ever truly meet across the gulf of space, it is not enough for both of them to exist. They have to exist at the same time. More than that, they have to be in the same brief, talkative phase of their existence at the same time, while also being close enough for any signal to cross the distance between them within that narrow window. And the galaxy has been turning for well over 10 billion years. A civilization's whole chatty era might last a few thousand years, or a few million if it is very fortunate. Against a 10 billion year backdrop, that is the thinnest sliver imaginable. The astronomer Frank Drake captured this beautifully back in 1961. In a famous equation he wrote out to organize the question of how many civilizations we might be able to talk to. The equation runs through all the hopeful factors, the number of stars, the fraction with planets, the fraction of those that could host life, and so on. But it ends on a single quiet term, often written simply as L, the lifetime. How long a communicating civilization lasts and keeps broadcasting. And it is that last term, the one about time, that quietly governs everything. You can fill the galaxy with planets and with life, and still hear nothing, if the windows never overlap. This is what some have come to call the Great Quiet, and it is worth pausing here to separate it from a much darker idea it is often confused with. You may have heard of the Great Filter, the notion that something out there reliably destroys civilizations before they can reach the stars. Some inevitable doom waiting for everyone, perhaps including us. That is a sharp, frightening argument, and it makes for dramatic late-night conversation. But it is not the gentle thing we are talking about tonight. The Great Quiet asks for no catastrophe at all. It needs no doom, no filter waiting in the dark. It only needs time to be vast, and windows to be brief, and the simple, almost arithmetic fact that brief moments scattered across an enormous span of years will rarely happen to coincide. The silence does not require that anything went wrong. It only requires that the universe is old, and that being alive and able to listen is a passing season, rather than a permanent state. And there it is, the quiet answer to the question in our title, stated plainly for the first time. The universe may be full of dead worlds, not because life is forbidden, and not because something hunts it down, but because the capacity to hold life is temporary. It arrives on a world, it lasts for a while, and then it fades, and these windows rarely line up. That is the why, not a single dramatic cause, but a soft and almost gentle truth about time itself. Habitability is a season. Worlds take turns having it, and the turns seldom overlap. We will spend the rest of tonight watching how that season opens and closes world by world. We will see the different ways it can end, some slow, some strange, some surprisingly close to home. But the thread running through all of it is this single idea, and it is worth carrying lightly rather than anxiously. We are not looking at a graveyard. We are looking at a calendar with many different years on it, and most of the interesting days falling on dates that never quite met. There is something steadying in that, if you let it settle. It means the silence is not a verdict. It is not the universe telling us we are alone, or that everything ends in ruin. It is simply what a vast and ancient cosmos sounds like when its living moments are scattered thinly across more time than we can really picture. The lights in the library went on and off at different hours. We arrived during one of the quiet ones. That is all. And of all the windows we could examine, the easiest to begin with are the two closest to home. We do not have to travel light years to find a finished world. We have two of them right here in our own solar system, near enough to study in detail. Two worlds that each had their season, and each lost it in a completely different way. The first one is the one we can actually see, written across its face in dry riverbeds and the ghosts of ancient water. Mars is the easiest dead world to talk about, because we can see how it died. Its whole face is a record of it. Through a good telescope, and far more clearly through the cameras of the spacecraft we have sent, you can trace dry channels winding across its surface, the unmistakable shapes of valleys cut by flowing water, river deltas fanning out where streams once emptied into standing lakes. The water is long gone, but the riverbeds remain, etched into the rust, like the lines on a face that remembers weather it no longer feels. For a long time, we read those lines wrongly, and the mistake is worth remembering with some tenderness, because it came from hope. In 1877, the Italian astronomer Giovanni Schiaparelli, peering through his telescope, mapped a network of fine straight lines across the Martian surface and called them canali, the Italian word for channels. But in English, that word slid easily into canals, and canals are not natural things. Canals are built. The American astronomer Percival Lowell took up the idea with great enthusiasm around the turn of the century, building an observatory in Arizona and sketching an elaborate network of waterways that he believed were the work of an ancient, intelligent civilization, a dying race on a drying world, channeling the last of their meltwater from the polar caps to feed their cities. It was a beautiful story, and we now know it was not true. The straight lines were a trick of the eye, the human mind connecting faint, scattered features into patterns that were not really there. There are no canals on Mars, and there is no dying civilization clinging to its last reservoirs. But buried inside that romantic error was a single instinct that turned out to be right. Lowell looked at Mars and saw a world that had once held water and then lost it. The details were wrong. The shape of the truth was not, because the Mars of tonight really is a world that lost almost everything. Stand on its surface, in your imagination, and feel how quiet it is. The average temperature across the planet hovers around 63 degrees below zero on the Celsius scale, cold enough that carbon dioxide itself can freeze out of the air at the poles. The atmosphere is so thin it barely deserves the name, less than 1% of the pressure we feel at sea level here on Earth. And there is no shield overhead. The surface lies open to the raw ultraviolet light of the sun, radiation that sterilizes the upper layer of soil, so that the reddish dust underfoot is not just barren, but actively hostile to the kind of chemistry life needs. It is a still, cold, scoured place, a world holding its breath, long after there was any breath left to hold. And yet, it was not always like this. That is the quiet heart of the Martian story. To understand what happened, we have to go down, beneath the dust and the frozen ground, into the center of the planet itself. When Mars was young, more than 4 billion years ago, its core was molten. A great churning sphere of liquid iron and nickel turned slowly at the planet's heart, hot from the violence of its formation. And a turning molten metal core does something remarkable. Its motion generates a magnetic field, a vast invisible structure that reaches up and out and wraps the entire planet in a protective shell. We call the engine that produces it a dynamo. Earth has one still, churning away beneath our feet right now, and it is the reason a compass needle points north. Young Mars had one too, and that magnetic shield did something quietly essential. It deflected the solar wind. The solar wind is easy to forget, because we never feel it. It is a constant thin stream of charged particles flowing outward from the sun in every direction, blowing past the planets year after year for the entire life of the star. It is gentle by the standards of cosmic violence, but it is relentless. And given enough time, it can strip a planet's atmosphere away, peeling off the lighter gases at the top and carrying them into space a little at a time. A strong magnetic field holds that wind at bay, parting it around the planet the way a stone parts a stream. While the dynamo turned, Mars kept its air. But Mars is small, and that single fact governs nearly everything about its fate. It is only about half the diameter of Earth, with far less mass packed inside it, and a smaller world cools faster. Think of a small stone and a large boulder pulled from the same fire at the same moment. The pebble loses its warmth quickly, while the boulder stays hot for hours. Mars was the pebble. Its modest interior could not hold its primordial heat the way Earth's larger body could. And as the core cooled, the churning slowed, and the dynamo began to fail. Our best current estimate is that the global magnetic field of Mars collapsed somewhere around 3.9 billion years ago, though I want to be honest that this number is still being refined. Recent studies of the faint magnetism frozen into the oldest Martian rocks, the kind of careful paleomagnetic work that reads a planet's magnetic history out of its stone, have nudged that timing one way and another, and the debate is genuinely active. The point is not the exact year. The point is the slow, unstoppable shape of it. The fire at the center of the world banked down, the churning quieted, and the shield that had wrapped the planet for hundreds of millions of years began, gently, to slip away. And once it was gone, the solar wind went to work. With nothing to deflect it, that thin, steady stream from the sun began stripping the Martian atmosphere from the top down, century after century, eon after eon. We are not guessing at this part. A NASA spacecraft called MAVEN, which arrived at Mars in 2014 specifically to study its upper atmosphere, has watched the process happening in real time. It has measured the air actively leaving the planet, charged particles being caught by the solar wind and carried off into the dark. What MAVEN sees today is the faint, final trickle of a process that, over hundreds of millions of years, drained away most of an entire world sky. It is worth pausing on the gentleness of all this, because there was no single catastrophe, no collision, no explosion, no sudden death. Mars did not end in violence. It cooled. Its inner fire faded, the way a hearth fades late in the evening when no one adds another log, and the room slowly loses its warmth long after the last flame has gone. The shield came down because the fire went out. The air left because the shield came down, and the water, no longer held by enough air and warmth to stay liquid, froze into the ground or escaped into space along with everything else. A whole world's habitable season closed, not with a bang, but with the quiet arithmetic of a small planet losing its heat to the cold around it. So that is how the air left Mars. But before it left, while the world was still warm and wet and wrapped in its protective shell, something was happening on the surface. There was standing water. There were lakes that lasted not for a moment but for ages, and the rocks at the bottom of those lakes have been waiting ever since to tell us what that warmer, wetter Mars was actually like. The rocks of Mars still remember the water. That is the strange and moving thing about a dead world. The body is cold now, but the record stays, pressed into stone, waiting for someone to come and read it. And in the last decade or so, we have finally sent readers. Settle into a particular place for a moment. Gale Crater, a wide basin near the Martian equator, with a mountain of layered rock rising from its center. In August of 2012, a NASA rover the size of a small car touched down there. Its name was Curiosity, and it has been climbing slowly through those layers ever since, reading them from the bottom up, the way you might read the pages of a book stacked oldest at the bottom. And what Curiosity found, layer after layer, was the unmistakable handwriting of water. It found mudstones, the fine-grained rock that forms only in still, quiet water, the kind that settles at the bottom of a calm lake over a very long time. It found clay minerals, which form when water works on rock gently and patiently. And it found the rounded, smooth pebbles that only running water can make, the same shapes you would find in any streambed on Earth, tumbled smooth by a current that flowed long enough to wear their edges away. Layer by layer, the story assembled itself. Gale Crater had once held a lake, not a brief puddle from a passing storm, but a real standing body of water that persisted, filled and dried and filled again, across what must have been millions of years. And here is the detail that quietly takes the breath away. While that lake stood on Mars, with rivers feeding it and sediment settling slowly to its floor, Earth was running almost the exact same experiment, at almost the exact same time. Our own planet, in that distant era more than 3 billion years ago, was a young world of warm, shallow seas, where the very first single-celled life was finding its footing. Two neighboring worlds, both wet, both warm, both wrapped in atmosphere, both sitting in the comfortable middle distance from the same sun. Two laboratories running side by side, each one given the same ingredients and the same long stretch of time. On one of them, the experiment took hold and never let go. On the other, it ran for its season, and then the world cooled, and the water vanished, and the lake at Gale Crater became a dry basin of layered stone, holding the memory of a wetter age. We do not know whether anything ever lived in that Martian lake. That is the honest center of all of this. But we know the lake was there, and that it lasted, and that the window during which Mars could have supported life on its surface was not a brief flicker. The best evidence suggests that window stayed open for hundreds of millions of years, a span long enough that, on Earth, life had plenty of time to begin during a comparable stretch. Mars had the warmth, it had the water, it had the time. And then, somewhere around 3 billion years ago, as the core cooled and the air thinned and the shield came down, that window quietly closed. To stand in front of those ancient lake beds is a peculiar feeling, and the closest thing I can compare it to is finding an old photo album in a dusty attic. The house is silent now. The people in the photographs are strangers to you, and the moments they captured are long past, but the faces are real. The afternoon light in the pictures really fell that way. The day really happened, even though no one is left in the house to remember it. That is what the rocks of Gale Crater are, a photo album of a warm, wet Martian youth. The images faded but genuine, the moments real, the house gone quiet. Which brings us back, gently, to the tube we began with tonight, because Curiosity is not the only rover reading the Martian rock. In February of 2021, a second NASA rover landed in a different basin, Jezero Crater, chosen precisely because it once held a lake fed by a river, with a delta still visible where that river spread its sediment across the crater floor billions of years ago. That rover is Perseverance, and it was there, in the ancient water-laid rock of Jezero, working on a stone the mission named Chayava Falls, that Perseverance found those pale leopard spots, ringed with darker edges, holding the Vivianite and the Greigite we talked about at the very start. Now we can set that discovery into its proper place. These spots sit in rock that formed in water, in a crater that held a lake, on a world that we now know ran the same warm and wet experiment that Earth did during the same era, before its season closed. That context is exactly why the markings are so tantalizing, and also exactly why we must stay so careful. The same minerals that microbes leave behind on Earth can also be produced by ordinary chemistry, by water and rock reacting together with no life involved at all. Both stories fit the evidence. We genuinely can't yet tell which one is true. This is why the team that published their findings in the journal Nature in September of 2025 chose the phrase potential biosignature and held to it, not life, not even probable life, a possible sign, the best candidate the mission has found, sealed inside that little tube called Sapphire Canyon, drilled and capped in the summer of 2024, now waiting in the cold of Jezero for a journey home that may not come until the late 2030s or beyond. It is the most delicate piece of evidence we possess about whether the experiment on Mars ever produced anything alive. And it is, for now, unresolved, suspended in that honest space between hope and proof, where good science is content to wait. There is something fitting in that patience. Mars kept it secret for 3 billion years. It can keep it a little longer while we figure out how to bring the answer home and read it properly. And whatever that answer turns out to be, the larger lesson of Mars is already written plainly across its surface, in every dry channel and every layer of lakebed stone. Here was a world that had everything it needed for a long and generous season, and then quietly lost it. The window opened, it held for a while, and it closed. That is one way a world can die. It can cool and let its air bleed away and let its lakes freeze into memory. But it is not the only way, and it is not even the most dramatic. To see another, we only have to turn around and look the other direction, toward the sun, at a world that did not freeze at all. A world that, by every measure that should matter, is Earth's near twin, and yet became something almost unimaginably hostile. A world that did not lose its water to the cold. A world that lost it to fire. Turn now toward the sun, to the second planet out, the one that shines so brightly in our morning and evening skies that we have called it the morning star and the evening star, and named it for the goddess of love. Venus. From a distance it is the loveliest point of light in the sky, steady and brilliant and pale gold. It is also, by every measure of its surface, the most hostile world in the solar system. And the reason that contradiction matters so much is that Venus had no business turning out this way, because Venus is, in almost every respect that should count, Earth's twin. It formed beside us, from the same swirling material in the same young solar nursery, at very nearly the same distance from the same star. It is almost exactly the same size as Earth, with about the same mass and the same rocky bulk. If you were assembling two planets and wanted them to come out the same, you could hardly choose two better candidates. Same ingredients, same neighborhood, same era, and yet one became a world of oceans and forests and breathing creatures, and the other became a furnace. To understand why is to understand a second, entirely different way that a world can lose its season. For a long time, we could only guess at what lay beneath the thick, permanent clouds that hide the Venusian surface. One of the earliest and most striking guesses came from a young Carl Sagan, who in the early 1960s used ground-based radio measurements to argue that the surface of Venus must be searingly hot, far hotter than anyone had wanted to believe. He turned out to be right, but the deeper surprise is not that Venus is hot now, it is that Venus may not always have been. This is where we have to be careful and honest, because the early history of Venus is not settled fact. It is a model result, a possibility that comes from running the physics forward on powerful computers, rather than from any rock we have held in our hands. Researchers at NASA's Goddard Institute for Space Studies, including the scientists Michael Way and Anthony Del Genio, have built detailed three-dimensional climate simulations of early Venus. And what some of those models suggest is remarkable. Given a slow rotation and the right kind of cloud cover, early Venus could have held liquid water, shallow temperate oceans, for as long as 2 to 3 billion years. Not a brief wet phase, but billions of years of mild ocean-bearing climate, sitting just sunward of Earth. I want to hold that claim gently, because it depends on assumptions that other models challenge. Some simulations suggest Venus was dry almost from the start, never cool enough for oceans to form at all, so this is not something we know. It is something we can credibly imagine, supported by serious peer-reviewed work and contested by other serious work. The careful way to say it is that Venus could have been a water world for a very long time. Whether it truly was remains an open question, and a fascinating one. But suppose, for tonight, that it was. What happened next is a process we understand very well, and it unfolds with a terrible patient logic. It is called the runaway greenhouse, and it is worth walking through slowly, because it is one of the most important mechanisms in all of planetary science. It begins with a small push in the wrong direction. Perhaps the sun, which brightens slowly over billions of years, grew just luminous enough. Perhaps a great wave of volcanic activity resurfaced the planet and loaded the air with gases. Whatever the trigger, the surface warmed slightly, and that warming caused a little more of the ocean to evaporate. Now, water vapor in the air is itself a powerful greenhouse gas. It traps heat. So the extra vapor warmed the planet a little more, which evaporated a little more water, which trapped a little more heat. Each turn of the cycle fed the next. On Earth, something always steps in to break that loop before it runs away. But on Venus, with the sun a touch closer and the conditions just so, nothing broke it. The feedback simply kept turning, warmer and wetter and warmer still, until the oceans did not merely warm, they boiled. Every drop of surface water rose into the sky as vapor, thickening the atmosphere into a dense, scalding blanket. And then came the final, irreversible step. High in that vapor-laden air, ultraviolet light from the sun split the water molecules apart into hydrogen and oxygen. The hydrogen, lightest of all elements, drifted up and escaped into space, lost forever. And once the hydrogen is gone, you cannot make water again. The ocean does not evaporate and wait to return when things cool. It is dismantled, molecule by molecule, and carried off into the dark. The world is left permanently, irrecoverably dry. What remains is the Venus we actually measure, and the numbers are sobering even spoken softly. The average surface temperature is around 462 degrees Celsius, hot enough to melt lead, hotter than the surface of Mercury, despite Venus being farther from the Sun. The atmospheric pressure at the surface is about 92 times what we feel here on Earth. To imagine that, picture diving down through our own ocean to a depth of roughly 900 meters, with all that water pressing in on you. That is the weight of the Venusian air. And drifting through that crushing, furnace-hot atmosphere are clouds, not of water, but of sulfuric acid. We know these conditions are real because we sent machines to stand in them. In the 1970s and early 1980s, the Soviet Union landed a series of probes on Venus, the Venera landers, in one of the most extraordinary feats of engineering in the history of spaceflight. They built craft to survive a place that destroys almost anything. And even those armored landers lasted only a little while on the surface, the longest of them holding out for roughly 2 hours before the heat and pressure silenced them. 2 hours, then quiet, on a world that was once, perhaps, as gentle as a shallow sea under a pale sky. If you have found something here worth sitting with tonight, the quiet story of 2 neighboring worlds and the different ways they lost their seasons, I would be grateful if you took a moment to follow along with Cosmic Drift. There is no rush, and nothing to interrupt the calm. Just a gentle way to let these journeys keep finding you, evening after evening, when you need somewhere soft to rest your mind. Because Venus and Mars together tell us something the night sky alone never could. Here are two worlds that began so differently, one too far and one too near, one ending in cold and one ending in fire, and yet both arriving at the same destination. Silence, a finished world, a season that opened, held for a while, and closed. Mars is what happens when the warmth runs out. Venus is what happens when there is too much of it, and Earth, by some delicate grace, sits between them. But Venus did not vanish without a trace. The oceans it may have lost left something behind, a faint chemical signature still hanging in its dry and poisoned air, a kind of fingerprint of water that is no longer there. It is one of the most beautiful and haunting details in all of planetary science, and it is where we turn next. There is a particular kind of trace that water leaves behind, even after it is gone, and it is one of the quietest and most extraordinary things we can read in the atmosphere of another world. The oceans of Venus, if they ever existed, did not simply boil away without leaving a single mark. They left a signature, hanging in the dry and acid air, that we can still measure today from across the solar system. A chemical ghost, and to understand it, we need to spend a moment with one small and beautiful fact about water itself. Water, as we learn early, is made of hydrogen and oxygen. Two atoms of hydrogen bound to one of oxygen, the simple recipe written into every drop of every ocean. But hydrogen comes in more than one form. Most hydrogen atoms are as light as an atom can be, a single proton and nothing more. But a small fraction of them carry an extra particle in their core, a neutron, which makes them about twice as heavy. This heavier form has its own name. We call it deuterium. It behaves chemically just like ordinary hydrogen, and it forms water just the same. So every natural body of water is a mix of the two, mostly the light kind, with a small, steady sprinkling of the heavy kind threaded through it. Now picture what happens when a world's ocean is lost the way Venus may have lost its own. The water rises into the atmosphere as vapor, and high above, sunlight breaks those molecules apart, and the freed hydrogen drifts upward and escapes into space. But here is the gentle physics that makes all the difference. The light hydrogen, being light, escapes more easily. It rises faster and slips away first. The heavy deuterium, being sluggish and harder to lift, lingers behind. So as the eons pass and the water leaves, the air does not simply empty. It changes its balance. With each measure of hydrogen lost to space, the proportion of heavy deuterium left behind creeps upward. The world keeps the heavy water longest. And if you could come back long after the ocean was gone and measure what remained, you would find an atmosphere strangely enriched in deuterium, as though someone had carefully poured off the light water and kept only the heavy. That is exactly what we find on Venus, when we measure the ratio of deuterium to ordinary hydrogen in the Venusian atmosphere, a number scientists call the D to H ratio. It comes out roughly 100 to 150 times higher than the same ratio here on Earth. Our oceans set Earth's value. Venus sits more than 100-fold above it, and there is really only one sensible way to read that. Venus once held a great deal of water, far more than the trace of vapor we see today, and it lost almost all of it to space over a very long time, keeping the heavy remnant as a kind of residue. This measurement is the single strongest piece of physical evidence that Venus was once a wet world. It is the fingerprint of an ocean that no longer exists. We did not arrive at this number by guesswork. It was built up over decades, from spacecraft and from telescopes. The American Pioneer Venus mission carried instruments into the Venusian atmosphere at the end of the 1970s. The European Space Agency's Venus Express orbited the planet through the 2000s and into the 2010s, refining the measurement. Ground-based spectroscopy added more. Each one read the same story in the air. The light water is gone. The heavy water remains. An ocean came and went and left its ghost behind. I find this one of the most moving ideas in all of planetary science, and it is worth letting it settle. A world can lose everything it had, its seas, its softer sky, its whole gentle season, and still leave behind a faint, readable trace of what it once was. Not a fossil in stone, but a fingerprint in the very air, written in the ratio of heavy water to light. An obituary hanging invisibly above a dead world, waiting for someone patient enough to read it. And now follow that thought outward, past Venus, past the edge of our solar system, into the wider field of stars we spoke about earlier. Because the same kind of signature does not have to stay in our own neighborhood, the next generation of space telescopes is being built precisely to read the chemistry of atmospheres around distant exoplanets, to take the faint light that passes through a far-off world's air and break it apart and study what it contains. And among the things such instruments may one day detect is exactly this: a heavy water signature, an enrichment of deuterium in some distant planet's atmosphere, hanging there as the quiet evidence that this world too once held an ocean it has since lost. Think of what that means. Light years away, around a star we will never visit, there may be a world that ran its own version of the Venus story, that warmed and brightened and boiled away its seas long before our species existed, and the ghost of that lost ocean is traveling toward us right now, carried in the thin sliver of starlight that filters through the planet's dry air, waiting for a telescope sensitive enough to catch it. We may someday read the obituary of a world we never knew was alive. From across a distance we could never hope to cross. We will not be able to go there, but we may be able to know. That is the gift Venus gives us, in the end. It teaches us how to recognize a finished world from far away by the trace it leaves in its own air. Mars showed us a death by cooling, written in dry riverbeds and the rust of a sterilized surface. Venus shows us a death by fire, written in the heavy water still hanging in its sky. Two neighbors, two utterly different endings, and the same quiet result. Two seasons that opened, held for a while, and closed. And between them, by a margin we are only beginning to appreciate, sits our own world. Not too cold, like Mars. Not too hot, like Venus. Resting for now in the narrow band where water can still pool on the surface and stay there. It is tempting to think of that as a fixed and permanent address, a safe and settled place in the order of things, but it is not fixed at all. The very band of safety that Earth occupies is slowly moving, drifting outward across the ages as the sun itself changes, and understanding that slow drift is the next part of our story, because it reveals something gentle and surprising. Habitability is not really a place. It is a moment. We tend to picture the habitable zone as a fixed ring. Open almost any diagram of a star and its planets, and you will see it drawn that way, a soft green band circling the star at a comfortable distance, with the words habitable zone printed neatly across it. It looks permanent, like a property line, like something painted onto the solar system at the beginning and left there ever since. It is one of the most useful pictures in astronomy. It is also, in a quiet and important way, not quite true, because the star at the center of that diagram is not a fixed thing. A star is a slow, steady engine of nuclear fusion, fusing hydrogen into helium in its core, and over the enormous spans of its life. That engine does not hold perfectly constant. It brightens, gradually, imperceptibly, across hundreds of millions and billions of years. A star like our sun grows more luminous as it ages, and as the star brightens, the comfortable band around it, the zone where water could stay liquid, slides outward. The green ring is not painted on. It is drifting slowly away from the star all the time. Our own sun is doing this right now. When the Earth was young, the sun was noticeably fainter than it is today, something like 70% as bright. Over the 4.5 billion years since, it has brightened by roughly 30%, and it continues to brighten by about 10% with every billion years that pass. This gentle fact carries a famous puzzle inside it, one that scientists call the faint young sun paradox. If the early sun was so much dimmer, the young Earth should have been frozen solid, a ball of ice. And yet we have clear evidence of liquid water and early life on the young Earth, under that fainter sun. Exactly how the early Earth stayed warm enough is still a subject of careful study, likely involving a thicker blanket of greenhouse gases in those ancient skies. But the fact that matters for us tonight is simply that the sun was dimmer then and is brighter now, and will be brighter still. To feel what that slow brightening does, let me offer you the image we will carry through this part of the story. Imagine the keyboard of a piano, the long row of black and white keys running from the deep low notes on the left to the high bright ones on the right. Now imagine that the range where a planet can be habitable, where water stays liquid, is not the whole keyboard, but a single octave, one modest span of keys somewhere along it. That octave is the habitable zone, and as the star ages and brightens, that playable octave does not stay where it is. It slides slowly up the keyboard, drifting away from the star a little further with every passing age. Now watch what happens to the planets as the octave slides. They do not move. Each world stays in its own orbit, holding its own note, more or less where it was born. But the playable range moves across them, and so a planet that once sat comfortably within the octave can find, over billions of years, that the octave has slid past it, and it is no longer in the playable range at all. This is the deeper story of Mars and Venus, told from a new angle. When the sun was younger and fainter, the playable octave sat closer in. Mars, out at its greater distance, may have rested near the cooler, lower edge of that early range, cold, but not impossibly so, warm enough for a time to hold its lakes. But Mars's tragedy was not really the moving octave. Mars was small, and it lost its inner heat and its magnetic shield and its air before the brightening sun could do it much good. It fell off the playable range from below through its own cooling, while the octave was still sliding toward it. It is a reminder that a world can leave the habitable season by more than one door at once. Venus tells the cleaner version of the octave story. Venus orbits closer to the sun than we do, and when the sun was fainter, that closeness may have been just right, placing Venus comfortably within the early playable range, warm enough for those possible oceans we spoke of. But as the sun brightened across the eons, the hot upper edge of the octave crept inward toward Venus, and eventually overtook it. The note that Venus held, once squarely inside the playable range, fell off the high, bright end. The water vapor built, the feedback turned, and the runaway greenhouse did the rest. Venus did not move. The octave slid up the keyboard and left it behind on the burning side. And Earth? Earth sits near the middle of the playable octave today, holding a clear and comfortable note, neither near the cold lower edge nor the hot upper one. That is the grace of our present moment, but the keyboard is still in motion. The same slow brightening that overtook Venus is, very gradually, sliding the octave outward across us too. We are not near the edge now, but now is the operative word, because the octave does not stop sliding just because we have grown fond of our place on it. There is something clarifying in seeing it this way, and I do not mean it as a frightening thought, because it is not one. It simply reframes what the habitable zone really is. It is not a safe address that a planet either has or does not have. It is a passing alignment between where a world happens to orbit and where the star's slowly drifting octave happens to fall at a given moment. Be in the right orbit at the right age of the star, and you hold a playable note. Stay in that same orbit long enough, and the music moves on without you. This is the quiet mechanism beneath so much of what we have been circling tonight. We keep returning to the idea that habitability is a season, rather than a permanent state. And here is one of the clearest reasons why. The window is fragile not just because cores cool, or atmospheres escape, or greenhouse loops run away, though all of those are real. It is fragile because the very definition of the safe zone is in motion, always drifting outward as the central star burns through its long life. A world can do everything right, hold its air and its water and its magnetic shield, and still simply be left behind as the playable range slides past it, which leads to a gentle and almost startling consequence, one that reshapes how we ought to think about every distant world we find sitting in a habitable zone. If the zone is always moving, then finding a planet inside it tells us far less than the headlines suggest. It tells us where that world stands at this one particular moment in the long life of its star. It tells us nothing about whether the moment came too early or arrived too late, or has already quietly passed. And that, as we will see, may be one of the deepest reasons the Great Library stays so quiet. A planet sitting in the habitable zone is a snapshot, not a portrait. That is the quiet realization waiting at the end of the sliding octave, and it changes how we ought to read every hopeful headline about a distant world in the comfortable band around its star. When we find such a planet, we have learned something real and worth knowing, but we have learned where it stands in a single instant of a story that runs for billions of years. We have caught one frame of a very long film, and we are tempting ourselves to guess the whole plot from it. To see why that matters, it helps to add a second dimension to how we think about these worlds. We have grown comfortable asking where a planet is. Is it close to its star or far? Is it inside the habitable band or outside it? But the sliding octave teaches us to ask a different and harder question alongside the first one, not just where a world is, but when it is. At what point in the long life of its star are we catching it? Near the beginning, while the octave is still sliding toward it, in the middle, holding a clear note, or near the end, with a playable range already drifting past. Because a world that sits squarely in the habitable zone today might be telling us almost anything about its real history. It might be a young world, only now arriving at the playable range, its surface still too cold, its ocean still locked in ice, waiting for the brightening star to bring it into the music a billion years from now. Or it might be an old world, one that held its season long ago and lost it, with oceans that boiled away an age before we ever turned a telescope toward it, now sitting in the slot purely by the accident of where the moving zone happens to fall. The same snapshot, a planet in the green band, can hide a world that has not yet begun. a world in the middle of its prime, or a world whose prime is long finished. From a single frame, we often cannot tell them apart. This is the temporal mismatch, and once you see it, the silence of the great library starts to make a deep and gentle kind of sense. Imagine a single star system with several rocky worlds spread out at different distances. As the star ages and the octave slides outward, it could pass over each of those worlds in turn. The innermost world holds its habitable season first, early in the star's life, and loses it as the zone moves on. Ages later, a middle world comes into the playable range and has its own long season. Ages after that, an outer world, once frozen, finally warms into the music as the aging star brightens. One system, 3 habitable worlds across its history. And yet, at any single moment you might choose to look, perhaps only one of them is in its season, and quite possibly none. That is the heart of it. A star system can host habitable worlds plentifully across time, and still almost never host 2 of them at the same time. The seasons are real, but they are staggered, handed from one world to the next down the long corridor of the star's life, the way a single spotlight might travel slowly across a stage, lighting each actor in turn, but rarely 2 at once. And if even neighboring worlds around the same star take their turns rather than sharing them, how much more staggered must the seasons be across the whole vast galaxy, with its hundreds of billions of stars each running its own slow sequence on its own schedule. This is why being in the habitable zone, that phrase we hear with such excitement, promises so much less than it seems to. Most of the worlds that are ever habitable across all of cosmic time are not habitable now. They had their season in the deep past, or they are waiting for it in the far future. The galaxy is full of worlds in the wrong era of their own star's life, worlds that arrived too early or stayed too late, standing in the right place at precisely the wrong time, not ruined, not cursed, simply out of step with their moment, the way you might arrive at a beloved place in the wrong season, finding the garden bare or the festival already packed away. And here, gently, is the title's quiet answer growing fuller. The universe may be full of dead worlds and silent ones, not because life is rare or forbidden, and not because some catastrophe stalks every world that reaches for the stars. It may be full of them simply because the window of habitability opens and closes, and these windows rarely line up, not across the worlds of a single star, and far less across the immense reach of the galaxy. A world being capable of life is a passing alignment in time, and the alignments scatter thinly across more years than the mind can hold. The silence is not a verdict on life. It is the sound of a great many brief seasons that never quite overlapped. There is a strange comfort hidden in that if we let ourselves find it. It means the quiet is not loneliness in the way we feared. It is more like the quiet of a long relay that has been running since before the earth formed, each world carrying the possibility of life for its own stretch, and then passing it onward as its season ends. We are not the only runners. We are simply the ones holding the light at this particular moment, in this particular corner of the track. Others held it before us, around stars long dead. Others will hold it after, around stars not yet born. We just cannot see them, because their moments and hours fall on different pages of a calendar billions of years long. So far, every world we have followed has orbited a star much like our own, a steady, moderate yellow sun, of the kind we naturally picture when we imagine a habitable planet, and when we read about Earth-sized worlds in the habitable zones of distant stars. The image that rises in the mind is almost always another gentle yellow sun, warming another quiet blue world. But that image, comforting as it is, turns out to be the exception rather than the rule. Most of the stars in the galaxy are nothing like our Sun at all. They are smaller, cooler, far more numerous, and a great deal less gentle. And most of the habitable zone worlds we are actually finding orbit those restless little stars, which is where our story turns next. When we imagine another habitable world, we almost always imagine another sun like ours hanging in its sky. A warm, steady yellow star pouring down even light on a quiet blue planet. It is a lovely picture, and it is the one that rises naturally whenever we hear that an Earth-sized planet has been found in some distant habitable zone. But it describes the rarer kind of star, not the common one. If you could take a true census of the galaxy, counting every star one by one, you would find that our Sun belongs to a minority. The most common stars by far are something else entirely. They are called red dwarfs, or in the more technical language, M dwarfs. They are small, cool, dim stars, far less massive than our Sun, glowing a deep reddish color because their surfaces are so much cooler. And they are, simply by their numbers, the great majority of the galaxy's population. Roughly 3 out of every 4 stars in the Milky Way are red dwarfs. For every sun-like star you picture, there are several of these smaller, cooler ones, far more numerous, far longer lived, and far less serene. This matters enormously for our search, because most of the habitable zone planets we are actually finding orbit these little stars. The reason is partly about the stars themselves, and partly about how we hunt. A red dwarf is so dim that its habitable zone, the band where water could stay liquid, sits very close in, far nearer to the star than Earth is to the Sun. A planet has to huddle close to a red dwarf to feel enough warmth, and a planet that orbits close has a short year, whipping around its star in days or weeks, and crosses in front of it often, which is exactly the signal our telescopes are best at catching. So when we find a small world in the habitable zone of its star, more often than not, it is circling a red dwarf. These are the worlds the headlines describe, and they come with complications that a gentle yellow sun does not impose. The first is a strange and quiet one. A planet orbiting that close to its star is likely to become tidally locked. The star's gravity grips it so firmly that the planet's rotation falls into step with its orbit, and it ends up keeping one face turned permanently toward the star, the way our own moon keeps one face turned always toward Earth. On such a world, there is no sunrise and no sunset. One hemisphere lives in endless daylight, baked under a sun that never moves from the sky. The other lies in perpetual night, a cold and starless dark that never lifts. Between them runs a thin band of permanent twilight, a ring of eternal dawn circling the whole planet, where the light comes in low and level and never changes. Whether life could find a home along that twilight ring is a real and open question, and a fascinating one. But it is a far stranger kind of world than the gently turning one we know. The second complication is the one that gives this part of the story its character, and it is where we have to choose our words with care, because it would be easy to make it sound frightening, and the truth is more interesting than fear. Red dwarfs are not steady. Our Sun is a remarkably calm star, glowing with an even, reliable light across the ages. Red dwarfs, especially when they are young, are restless. They flare. They build up magnetic tension in their churning interiors and release it in sudden bursts of radiation, brilliant flares that can briefly outshine the quiet star many times over, washing the close-in planets in a wave of high-energy light and charged particles, We have watched this directly, and the clearest view has come from one particular system. About 40 light-years away sits a small red dwarf called TRAPPIST-1, remarkable for hosting not one but 7 Earth-sized worlds, several of them in or near the habitable zone, making it one of the most studied planetary systems we know of. The James Webb Space Telescope has turned its instruments toward TRAPPIST-1, and the picture that has emerged is of a busy, active little star. The flare data, recorded by Webb in 2022 and 2023, and carefully analyzed in studies published in 2025, point to a star that flares often. Depending on exactly how large a flare you count, the rate works out to something on the order of several flares a day, with one 2025 analysis finding a few large flares each day at a particular energy threshold, far more frequent than earlier predictions had suggested. A planet huddled in close to a star like that does not bask in steady warmth. It is repeatedly bathed in bursts of radiation, again and again, day after day, for the long life of the star. So instead of imagining a steady hearth, the image to hold for a red dwarf is something more like a flickering porch light. Not a warm, constant glow you can settle beneath, but a light that surges suddenly bright, then dims, then surges again, never quite letting the moths beneath it settle into stillness. The warmth is there. The trouble is that it will not hold steady, and the surges carry a sting. What those repeated flares do to a planet's prospects for life is genuinely uncertain, and honesty here matters more than drama. A young, active red dwarf could, over time, strip away the atmosphere of a close-in world, peeling off its air with each burst of radiation and stellar wind, leaving the surface exposed. Or a planet with a strong magnetic field and a thick enough atmosphere might weather the storms and hold on. We do not yet know which fate is the common one, and it likely differs from world to world. As a point of reference, here on Earth there is a microbe called Deinococcus radiodurans, famous for surviving doses of radiation that would kill almost anything else. A reminder that life can be astonishingly tough when it has to be. But laboratory results on whether flare radiation would sterilize a planet's surface vary from study to study, and it would be dishonest to pretend the question is settled. Some atmospheres may survive. Others may be stripped bare. The truth, for now, sits in between. What we can say plainly is gentler and more sobering at once. Most of the galaxy's worlds, most of our lottery tickets in the search for life, are issued not for the calm, steady stars like our sun, but for these small, restless, flaring ones. 3 out of 4. The most common kind of habitable real estate in the universe comes attached to a porch light that keeps surging and going dark, a star that may never quite let a world settle into the long, even calm that life on Earth has enjoyed. It does not mean those worlds are barren. It means the most common conditions for a planet in the universe are harsher and less steady than the rare, quiet circumstances we happen to have been given. And that quiet fortune of ours, the steady star and the gentle light, can make it easy to think of Earth as the safe and settled exception, the one world that simply got everything right and held it. But our own planet's history tells a more complicated story. Earth has come closer to losing its season than we usually like to remember more than once, and not always from anything out in the sky. Sometimes the threat came from within, and that is where we turn next, to the near endings of the one world we know for certain was alive. It is tempting to think of Earth as the steady one. After Mars and its slow cooling, after Venus and its runaway heat, after the restless flaring of the red dwarfs, our own world can seem like the calm exception in all of it, the planet that simply got things right and has held them steady ever since. We have had liquid water for billions of years, We have an atmosphere, a magnetic shield, a gentle and reliable star. Set beside its neighbors, Earth looks less like a world that survived and more like a world that was never really in danger. But that picture is gentler than the truth. The history written in Earth's own rocks is not a story of uninterrupted calm. It is a story of survival, of a thread that was very nearly cut, not once, but at least 5 separate times. These are the events we call the mass extinctions, the moments when life on Earth came suddenly and dramatically close to collapse. They are read out of the fossil record, where whole communities of living things appear in the layers of rock for a long stretch and then, at a certain boundary, mostly vanish, replaced over time by something thinner and sparser. Geologists have identified 5 of these great losses in the deep past, sometimes called the Big Five. And they are not abstractions. Each one was a time when an enormous fraction of everything alive on the planet quietly disappeared from the record, leaving the survivors to rebuild from whatever remained. The 5 are scattered across the last 500 million years or so, each one a marker in the long story of complex life. The first came around 444 million years ago, near the end of a period called the Ordovician. Another followed in the late Devonian, roughly 372 million years ago. A fourth came at the end of the Triassic, around 201 million years ago. And the most familiar of all, the fifth, struck about 66 million years ago, at the end of the Cretaceous, when a great asteroid impact closed the long age of the dinosaurs and cleared the stage for the rise of the mammals, and eventually for us. But the largest of them all, the one that came closest to ending the whole experiment, was the third. It happened around 252 million years ago, at the boundary between the Permian and the Triassic periods, and it dwarfs the others in scale. By the best estimates, something on the order of 96% of all marine species vanished. Not 96% of individuals, but 96% of the kinds of living things in the sea, gone. On land, the losses were nearly as severe. Life on Earth had never come so close to simply ending, and it has never come so close since. If you wanted a single moment when the thread of life on this planet was worn down to its very last fibers, this was it. What caused it appears to have been a slow catastrophe of the planet's own making. Rising from deep within, in what is now Siberia, an immense and prolonged episode of volcanic activity, known as the Siberian Traps, poured staggering volumes of lava and gas across the land over a very long span. The gases released into the air and oceans set off a cascade of changes. The climate shifted rapidly. The oceans warmed and acidified and lost much of their oxygen. The chemistry that life depended on came undone, gradually and then thoroughly, until most of it could no longer hold on. It was not a single blow from outside, like the later asteroid. It was a long, internal unraveling, the planet itself changing faster than its living things could follow. And yet, even at its worst, this was not a sudden apocalypse in the way we might picture one. These great extinctions, even the largest, generally unfolded across spans of time that stretch beyond anything human eyes could watch. Thousands of years, often far longer. So it is worth resisting the image of a single fiery instant and reaching instead for something quieter. Picture a great stage at the close of a performance, with the house lights slowly dimming, not snapped off all at once, but lowered gradually, scene by scene, until most of the stage stands in shadow, and only a few figures remain, faintly lit, waiting in the dark. The lights go down. They stay down for a long while. And then, slowly, over ages, they begin to come back up, and a new cast steps into the light, and the performance resumes, changed, but going on. That is what each of these resets really was. The thread of life narrowed almost to nothing, down to a few hardy survivors, the ones that could endure the cold or the heat or the empty oceans. And from those few, life slowly diversified again, refilling the world over millions of years with new forms built from the old. After the Great Permian extinction, the long recovery eventually gave rise to the dinosaurs. After the dinosaurs were cleared away by the asteroid, the recovery eventually gave rise to us. Every cast that walks the stage today stepped into the light after a previous one had mostly left it. The dimming and the slow return are not interruptions to the story of life. They are the rhythm of it. There is something steadying in seeing it this way, rather than as a series of disasters narrowly survived. Earth's living history is not a smooth and guaranteed ascent. It is a thread that has frayed nearly to breaking again and again, and been carried forward each time by the narrowest of margins, by whatever could hold on through the dark. We tend to think of our world as the safe success story, the one that proves a planet can keep its season indefinitely. But even here, on the one world we know for certain held life, the season has come close to closing more than once. The light has dimmed nearly to black and slowly risen again, 5 times over. And all 5 of those great resets, severe as they were, share something in common. They came, broadly, from forces we might call external to life itself, from volcanoes and shifting climates and a wandering asteroid, from the planet and the sky acting upon the living things that happen to be there. But there is one more near ending in Earth's deep past that does not fit that pattern at all. The most transformative crisis our world ever faced did not come from the sky or the depths of the earth. It came from life itself. It was caused by living things, doing nothing more than living. And it is one of the strangest and most beautiful stories our planet has to tell. The most dangerous thing that ever happened to life on Earth was life learning to breathe out. That is the strange turn at the heart of this part of the story, and it is worth approaching slowly, because it overturns something we take entirely for granted. The oxygen in the air around you right now, the gas you have been quietly drawing into your lungs through this whole long evening, the thing your body cannot live for more than a few minutes without, was once the deadliest poison the planet had ever known. It very nearly ended life on Earth, and the creatures that released it had no idea what they were doing. To understand this, we have to picture an Earth that almost no longer feels like Earth. Go back more than 2 billion years, and the planet is alive, but in a way we would scarcely recognize. There are no plants, no animals, nothing you could see with the naked eye. Life consists entirely of single-celled microbes, drifting and multiplying in the warm, shallow seas and the muds beneath them. And the air above those seas is nothing like the air we breathe. It holds almost no free oxygen at all. Instead, it is a mixture of other gases, carbon dioxide and methane and more, an atmosphere that would suffocate nearly every living thing alive today within minutes. This was the world for a very long time, far longer than complex life has existed since. Those early microbes were anaerobic, meaning they lived without oxygen, and to them oxygen was not merely useless, but actively destructive. It is a highly reactive gas. It tears at the delicate chemistry of cells that are not built to handle it, corroding them from within. For these organisms, free oxygen was a corrosive threat, the way harsh bleach is a threat to living tissue. And for 2 billion years, they had little to fear from it, because there was almost none of it around. They ruled a quiet, oxygen-free world, longer than anything has ruled the earth since. Then something changed, and it changed everything. Among those microbes, a particular kind found a new way to make a living. We call them cyanobacteria, and they worked out the trick of photosynthesis, of taking sunlight and water and carbon dioxide and turning them into energy and the building blocks of life. It was an extraordinary innovation, the same fundamental process that green plants use today, and it let the cyanobacteria flourish as never before. But photosynthesis has a byproduct, a piece of waste the process throws off and discards. That waste was oxygen. The cyanobacteria were not trying to change the world. They were simply living, simply feeding on sunlight and breathing out, as a matter of pure chemistry, the gas that would transform the planet. At first, the oceans absorbed it quietly. The early seas were rich in dissolved iron, and oxygen reacts eagerly with iron. So as the cyanobacteria released their oxygen, the iron in the water seized it, rusting, forming iron oxides that settled slowly to the sea floor. This went on for ages, the oceans drinking up the new oxygen as fast as it was made, locking it away in great layered deposits of rusted rock. We can still read those deposits today. They are called banded iron formations, alternating bands of iron-rich rock laid down across this immense span of time, and they are the recorded fingerprint of a world quietly rusting from the inside. For a long while, this kept the oxygen in check, and the air stayed much as it had always been. But the iron sinks could not last forever. Eventually, across hundreds of millions of years, the oceans had taken up about as much oxygen as they could hold, and once the seas were saturated, the oxygen the cyanobacteria kept producing had nowhere left to go. So it began to escape into the air. Around 2.4 billion years ago, free oxygen started to accumulate in Earth's atmosphere for the first time, building up gradually until the very composition of the sky had changed. We call this transformation the Great Oxidation Event, and it was, by any honest measure, one of the most consequential things that has ever happened to this planet. For the anaerobic life that had ruled the Earth for 2 billion years, it was a catastrophe. The rising oxygen, harmless to the cyanobacteria that made it, was poison to vast numbers of the old microbes that could not tolerate it. As it filled the seas and then the air, it corroded and killed them across the planet, a silent dying with no fire and no flood, just a slow change in the chemistry of the world that the existing inhabitants could not survive. It was, in effect, the first great extinction Earth ever knew, and life itself had caused it. How much of the old anaerobic world was lost, we genuinely cannot say. The fossil record from that far back is far too sparse and too damaged to give us a percentage. It was an enormous die-off of unknown scale, a quiet planetary poisoning whose exact toll is lost to time. And what followed has its own strange gentle name. After the Great Oxidation Event, the Earth settled into an extraordinarily long and quiet stretch, a period so uneventful in the record that scientists have nicknamed it the Boring Billion. For something close to 1 billion years, the planet seems to have changed remarkably little, neither advancing dramatically nor collapsing. A long, slow recovery and rebalancing after the Great Transformation. Life endured, adjusted, and waited, in no apparent hurry, for the next chapter. It is a humbling thing to consider that 1 billion years, longer than complex animals have existed, could pass in such relative stillness. But the deepest part of this story is the one worth sitting with as it closes. The oxygen that nearly ended life did not stay an enemy. Over the long ages that followed, some lineages of life did more than merely survive the new gas. They learned to use it. Oxygen, it turns out, is a far richer source of energy than the older chemistry could offer, and the organisms that learned to harness it gained an enormous advantage. That capacity, born from a planetary poisoning, is what eventually made possible everything large and complex and active that has ever lived. Every animal, every plant, every breath drawn by every creature that ever moved across this world, including the one you are drawing right now. The catastrophe became the foundation. The poison became the air. There is a quiet tenderness in that, and it ties back to the thread we have followed all evening. Here is yet another way a world season can turn, not from a cooling core or a brightening star or a wandering asteroid, but from life itself, reshaping its own world so completely that the inhabitants could no longer recognize it. Even on the one world we know held life, life nearly closed its own window and then slowly opened a wider one. The window of habitability is fragile in more ways than we usually imagine, and one of those ways is that the living things within it can change everything simply by living. Habitability, we keep finding, is not a guarantee. It is a balance, and the balance can be tipped from any direction, even from inside. So a world can be capable of holding life and still have life never take hold. And a world can hold life that nearly undoes itself, which raises a question we have been circling all evening without quite naming, and it is time now to look at it directly. There is a real and profound difference between a world that could support life and a world that actually does. The gap between those two things is one of the deepest mysteries we have, and it is where our story turns next. We use two words almost interchangeably, and they are not the same word at all. Habitable, inhabited. They sit so close together in the language that we let one slide into the other without noticing, so that a planet found in the habitable zone of some distant star can feel for a moment like a planet with someone on it. But the gap between those two words is one of the widest and most mysterious gaps in all of science. And tonight, it is worth holding them apart and looking carefully at the space between them. The cleanest way I know to feel the difference is to think of soil and seed. Habitability is the soil. It is good ground, fertile and ready, warm and moist and capable of supporting something that grows. Inhabitation is whether a seed ever actually fell into that soil and took root. And the crucial, humbling truth is that good soil does not guarantee a single growing thing. A field can be perfectly fertile and stand empty for 1,000 years simply because nothing was ever planted there. When we find a habitable world, we have found good soil. We have learned nothing at all about whether anything ever grew in it. This matters so much because of a peculiar limitation in everything we think we know about life in the universe. We have exactly one example of it. One. Earth and Earth alone is the only place we have ever confirmed that life exists. Every living thing we have ever studied, every microbe and fungus and fish and forest, every human being who has ever lived, belongs to that single example, that one data point. And a single data point is a strange and slippery thing to reason from. It tells us, with absolute certainty, that life is possible, because here we are. But it tells us almost nothing about how likely life is, how readily it arises, how often that fertile soil actually grows something. From one example, we cannot tell whether life is the natural and near inevitable response of any warm, wet world, or whether it is a fluke so rare that it may have happened only here, in all the vastness. There is a subtle trap hidden inside our one example, and it is worth naming gently because it shapes how we ought to think about all of this. We exist on a world where life arose. Of course we do. We could only ever have found ourselves on such a world, because a world without life has no one in it to look around and ask the question. Our own existence cannot be used as evidence that life is common, because our existence was the precondition for anyone wondering in the first place. We are not a random sample. We are the one place guaranteed in advance to have come up with the answer yes. And that means the warm comfort of our own presence here tells us far less about the universe than it feels like it should. When we look closely at the early history of life on Earth, the mystery only deepens, because the timing is genuinely puzzling. Earth formed, cooled, and became capable of supporting life. And then, somewhere in the long stretch that followed, life appeared. The clearest early traces, structures called stromatolites, layered mounds built up by communities of microbes, show up surprisingly early, suggesting that once conditions allowed, life may have arrived fairly quickly. But the records from that far back are faint and difficult to read, and the honest range for the gap between Earth becoming habitable and life first appearing stretches anywhere from almost immediately to several 100 million years. We cannot pin it down, and that uncertainty sits right at the center of the question, because if life arose quickly here, it might suggest that life arises easily wherever it can, or it might just mean that on the one world where we know it happened to happen soon. With a single example, even the timing refuses to settle the matter. This is the great unresolved divide among the scientists who study the origin of life, the leap from lifeless chemistry to the first living thing, a leap given the name abiogenesis. On one side stand those who suspect that life is, in some sense, a natural chemical tendency of the universe. Give a world the right ingredients, liquid water, the common elements, energy flowing through the system, and enough time, and the chemistry will, sooner or later, organize itself into something alive. In this view, life is less a miracle than a reflex, an almost expected outcome wherever the soil is good. The galaxy's billions of habitable worlds would then be billions of fields where seeds fell readily, and life would be common, scattered everywhere conditions allowed. On the other side stand those who suspect the opposite, that the step from chemistry to life is staggeringly improbable, a threshold so unlikely to be crossed that it might happen only once in an entire galaxy, or once in a far greater span than that. In this view, the fertile soil is everywhere, but the seed almost never falls, or almost never takes when it does. Life would then be precious beyond reckoning, a near impossible event that happened, as far as we can tell, here and perhaps almost nowhere else. And the most honest thing anyone can say is that we do not know which of these views is closer to the truth. Both are held by serious people. The evidence we have, our single example, is consistent with either. So the image to carry from here is exactly that, a seed and the ground it might fall on. Picture two seeds. One drifts down onto rich, deep, welcoming soil, settles in, and grows without difficulty. The other falls instead onto bare stone, where there is no purchase, no crack, no soil to take root in, and it simply rests there, never growing, no matter how long it waits. The question that haunts the search for life is which of these pictures describes our universe. Are the habitable worlds rich soil, where life springs up readily wherever it can? Or are they bare stone, fertile in principle, but almost never actually green, with our own world the one impossibly lucky seed that found a crack? We do not know. We have one seed, and it grew, and that single fact, remarkably, cannot tell us which world we live in. It is a strange place to arrive, this honest not knowing, but there is something clarifying in it rather than frustrating. It means that all those habitable worlds we have counted, the tens of billions of orbital slots where water is not ruled out, remain genuinely open questions. Every one of them. Each could be empty good soil, or each could be quietly green. The library may be full of books no one ever wrote, fertile pages that stayed blank, or it may be full of stories we simply have not learned to read. The uncertainty is not a failure of our science. It is the truthful shape of what a single example can and cannot tell us, and it leads to one more difficult and beautiful limitation, the one that closes this part of our journey. Even if life is out there, even if some of those distant worlds are quietly green, we are confronted with a humbling fact about distance and our place in the cosmos. We may be able to find the signs of life on a faraway world. We may even someday be reasonably sure of them, and we may still never be able to reach across the gulf to touch what we have found. The worlds that might hold the answer are, for the most part, worlds we can never visit, and learning to live with that particular distance is where our story turns next. Some of the most promising places to look for life are also the hardest places to ever check. That is the quiet frustration waiting at the edge of our search, and it begins close to home, in our own solar system, with a handful of worlds that may be hiding oceans where we cannot easily look. When we picture liquid water in space, we tend to picture it on a surface, lapping under an open sky, the way Earth's oceans do. But some of the most intriguing water in our solar system is sealed away, far from any sky. Out among the moons of the giant planets, there are worlds that appear to hold vast oceans beneath shells of ice. Europa, a moon of Jupiter, is wrapped in a smooth crust of ice that very likely floats atop a deep, global ocean of liquid water, kept from freezing by the heat of Jupiter's relentless gravitational squeezing. Enceladus, a small moon of Saturn, does something even more remarkable. It vents great plumes of water vapor and ice out through cracks near its south pole, jets of ocean water spraying into space, telling us plainly that there is liquid water down there beneath the frozen shell. And Titan, Saturn's largest moon, is stranger still, a world with a thick atmosphere and actual lakes and rivers on its surface, though not of water. On Titan, it is so cold that the lakes are made of liquid methane and ethane, and whatever chemistry unfolds there, if any, would be exotic beyond our ordinary imagining. These are tantalizing places, and we have barely begun to check them. If life exists on Europa or Enceladus, it would be sealed beneath miles of ice, in a dark ocean we have never touched, and reaching it would mean drilling through a frozen crust on a distant moon, a task at the very edge of what we can imagine doing. If something stirs in the methane lakes of Titan, it would be a kind of life so unlike our own that we might struggle even to recognize it. We have flown past these worlds. We have dropped a probe onto Titan and tasted the plumes of Enceladus from a distance. But the oceans themselves, the places where anything might actually live, remain just out of reach, hidden and dark and waiting. And those are the easy cases, the ones in our own solar system, close enough to send a spacecraft to in a matter of years. When we turn to the exoplanets, the worlds around other stars, the distances become something else entirely, and the limitation becomes absolute. We cannot go to them. Not with any technology we have, and not with any we can realistically foresee. The nearest stars are years away at the speed of light, and decades or centuries away at any speed a spacecraft could actually reach. The worlds we have counted in their thousands and estimated in their billions are worlds we will almost certainly never visit. So if we are ever to know whether any of them holds life, we will have to learn it from a distance, from nothing more than the light that reaches us across the gulf. The astonishing thing is that this may actually be possible. We cannot travel to a distant world, but its light travels to us, and light carries information. When a planet passes in front of its star, a thin sliver of starlight filters through the planet's atmosphere on its way to us, and the gases in that atmosphere leave their fingerprints in the light, each one absorbing its own particular colors. By spreading that light out and reading it carefully, a technique called spectroscopy, we can begin to learn what a distant atmosphere is made of, from light years away, without ever leaving home. And among the things we might read there are the possible signatures of life. The key idea is something called chemical disequilibrium. An atmosphere left to its own devices tends to settle into a chemical balance, its gases reacting until they reach a stable, unchanging mixture. But life disrupts that balance. It continually produces gases that should not coexist, that would normally react with one another and disappear, and yet persist because something keeps making them. The clearest example is our own air. Earth's atmosphere holds both oxygen and methane in significant amounts, and those two gases react with each other, so they should not both be abundant at once. The only reason they are is that life keeps replenishing them, constantly, faster than they can cancel each other out. An atmosphere caught in that kind of persistent imbalance is a strong hint that something is alive beneath it. So when our telescopes search distant exoplanets for the combination of oxygen and methane, or for other gases in disequilibrium, they are searching for the chemical exhaust of life itself. To feel both the promise and the heartbreak of this, it helps to turn the telescope around and imagine someone else holding it. Picture an astronomer on a world 100 light years away, looking back toward our sun, catching the faint light of Earth as it crosses in front of it. They spread that light out and read it, and they find something striking, an atmosphere rich in oxygen, laced with methane, held in exactly the kind of persistent disequilibrium that chemistry alone cannot explain. From that reading, this distant observer could conclude, with real confidence, that the third world, from that yellow star, almost certainly hosts a biosphere. They would know, across 100 light years, that Earth is alive, and then they would be stopped, exactly as we are stopped, by the same impossible distance. They could know we are here, and never reach us, never speak to us, never confirm with their own instruments what their readings so strongly suggested. They would be separated from the living world they had found by a gulf of space that no signal of theirs, and no ship, could cross within any lifetime that mattered. That is the peculiar shape of what we are likely to find, not contact, not conversation, but knowledge at a distance, the strong suggestion of life on a world we can study only as a point of filtered light, a possibility we can raise but never quite close. We may, in the coming decades, with the next generation of great telescopes, find an exoplanet whose atmosphere whispers of biology, oxygen and methane hanging together where they should not, the chemical signature of something alive, and we will stand here, light years away, able to read the whisper and unable to answer it, a locked case with something beautiful inside it, the glass clear enough to see through and far too thick to ever break. There is a particular kind of peace to be made with that, and it is worth making gently. We have spent this evening learning that habitability is a passing season, that worlds take their turns and rarely overlap, that the line between a habitable world and an inhabited one is a mystery we cannot yet solve. And now we add the last of these quiet limits, that even the worlds we might someday know to be alive will likely stay forever beyond our reach, glimpsed in their light and never in their substance. It could feel like a wall, but it can also feel like something softer, a reminder that knowing a thing is real and being at peace that you cannot hold it is its own kind of relationship with the universe. We can love what we cannot touch. We can wonder at what we will never reach. And that brings us toward the close of our long journey tonight, to the deepest and gentlest realization of all, the one that reframes the entire silent sky. Because all of this, every distant world and every faint signature, reaches us only as light, and light we are about to see is always news from the past. The sky we look up into is not a picture of how things are. It is a record of how things were, arriving all at once, from 1,000 different moments scattered across the depths of time. The sky is not a photograph. We have circled this idea all evening, and now it is time to rest in it fully, because it is the gentlest and most profound truth in our whole journey. When you look up at night, it feels as though you are seeing the universe as it is, right now, all those stars shining down on you tonight. But that is not what you are seeing at all. You are seeing light that left those stars long ago, each beam having traveled its own long road to reach your eyes. And because every star sits at a different distance, every point of light left its source at a different time. The night sky is not a single moment. It is countless different moments, gathered together and arriving all at once. Let us walk outward through those distances slowly, the way you might stroll a little further from home with each step, because the scale of it is a soothing thing to feel, rather than merely know. Start with the nearest light of all, the sun. Its light takes a little over 8 minutes to reach us, about 8 minutes and 20 seconds. So the sunlight warming the afternoon is always 8 minutes old. The sun you see is the sun as it was 8 minutes ago, and if it somehow winked out, you would have 8 unknowing minutes of light before the dark arrived. The present, even for our own star, is always slightly behind us. Step further out, past the planets, to the nearest other star. Proxima Centauri, the closest star to our sun, lies about 4¼ light years away. Its light takes more than 4 years to cross to us, so when you find it in the sky, you are seeing it as it was over 4 years ago. Step out again to Sirius, the brightest star in our night sky, about 8½ light years off. The Sirius you see tonight is the Sirius of 8½ years ago, its light having set out before some of the things you remember most clearly had happened. Already, looking up, you are looking years into the past, and we have barely left the neighborhood. Keep walking. The center of our own galaxy, the great crowded hub of the Milky Way around which everything slowly turns, lies some 26,000 light years away. The light arriving from there tonight left when the last ice age still gripped the earth, when our ancestors were painting on the walls of caves. 26,000 years crossing the dark to arrive at this single evening, and we are still inside our own galaxy, still close to home by cosmic measure. Step out past the edge of the Milky Way entirely, to Andromeda, the nearest large galaxy to our own. Andromeda lies about 2½ million light years away, and on a dark night you can just see it with the naked eye, a faint smudge of light. Let that settle for a moment. That faint smudge is light that left Andromeda 2½ million years ago, before our own species existed, when our distant ancestors were just beginning to walk upright on the African plains. You can stand in your yard tonight and catch, with your own eyes, light older than humanity itself. And we can go further still, far beyond what any eye could catch, to the deepest images our great telescopes have gathered. The James Webb Space Telescope has captured light from galaxies so remote that it left them more than 13 billion years ago, in the early ages of the universe, not long after the first stars began to shine. When we look at those faint, ancient smudges, we are looking almost all the way back to the beginning, seeing light that has been traveling for nearly the entire age of the cosmos to land, at last, on a single instrument built by a species that did not exist for all but the final flicker of that journey. Now hold all of those distances in your mind together and feel what they mean when they arrive at once. The 8-minute-old sunlight, the 4-year-old starlight, the 26,000-year-old glow from the galaxy's heart, the 2.5-million-year-old light of Andromeda, the 13-billion-year-old whisper from the edge of seeing, all of it landing on the same sky, on the same night, on the same upturned face. The sky you see is not one moment. It is every moment layered together, a single view assembled from 1,000 different pasts. This is why the word now loses its meaning when we speak across the distances of the cosmos. There is no shared present moment that stretches across the galaxy, no single instant that the whole universe occupies together. When you ask what is happening right now on a world 1,000 light years away, the question has no real answer we could ever know, because any news of that world is 1,000 years in coming, and any news of ours is 1,000 years in reaching it. Each place lives in its own present and sees every other place only in its past. The universe does not share a single tick of one great clock. It is a vast collection of separate moments, each one visible to the others only as it once was. So here, at last, is the image to carry home, the one we have saved for the end. The night sky is a mailbox, not a window onto the present, but a mailbox full of old letters, each one mailed at a different time from a different distance, all of them happening to arrive together tonight. Some of the letters are recent, sent only minutes or years ago. Some are ancient beyond imagining, sent before there were eyes to read them. And here is the tender part. Some of those letters come from senders who are no longer there. A star whose light reaches you tonight may have changed, or moved on, or ended its own long life in the centuries or millennia since that light set out. You are reading a letter from a house that may no longer stand, in handwriting from a hand that may be long still, and yet the letter is real, and the words are true, and they have crossed an unimaginable distance to find you. Exactly now, on this quiet evening. This is what makes the third door so peaceful rather than sad. We wondered, at the start, why the universe seems so silent if it should be so full. And here is the deepest part of the answer, gentle as anything we have touched tonight. The universe can be entirely quiet in this present moment and still be brimming with life across the whole sweep of time, because there is no single present moment that binds it all together. The worlds that had their seasons in the deep past sent their letters long ago, and we are only now receiving them. The worlds whose seasons are still to come have not yet written, and we sit in our own small present, holding a mailbox full of light from every era at once, unable to say which senders are still home and which have gone, only that the letters are beautiful and that they came. The library is not empty. It was never empty. It is simply that the readers came and went across more time than any one moment could hold, and the lights we see are the letters they left behind, glowing softly on the shelves, waiting to be read by whoever happens to be awake to read them. And tonight, that is us. We are the ones awake, holding the old light in the quiet. Which leaves one last question, the most personal of all and the most comforting. If the sky is a mailbox of letters from worlds in every stage of their long stories, from worlds that have ended and worlds not yet begun, then where in that great sequence do we stand? What stage of the story is Earth living through right now, tonight? And the answer, as we will see, is the gentlest place of all to find ourselves. We are not the exception. That is the quiet turn this whole evening has been moving toward, and it is far kinder than it first sounds. All through our journey, we have looked at finished worlds, at Mars gone cold and Venus gone hot, at the red dwarfs that never settle and the long resets that nearly ended life here. And through all of it, there has been an unspoken assumption keeping us company, the comfortable sense that Earth is different, that Earth is the one that got it right, the permanent success against a backdrop of failure, the world that stands outside the rule of passing seasons. But Earth does not stand outside that rule. Earth is simply the world that happens to be living through the middle of its season right now. And that is a far more beautiful thing to be than an exception. Let us lay out our own planet's timeline gently, the way we laid out the distances of the stars, because seeing it whole brings a strange and settling peace. Earth formed about 4.5 billion years ago. For most of the time since, it has held liquid water and life, somewhere on the order of 4 billion years of a living, breathing world. That is the long stretch behind us, the deep past of microbes and oceans, and the slow building of everything that came after, the oxygen and the resets, and the long climb to the complex life of today. 4 billion years of season already lived. That is the part of the letter that has already been written. And ahead of us lies the rest of it. And this is where we have to be careful and honest, and above all, calm, because the facts here are easy to misread as something frightening when they are nothing of the kind. The sun, as we learned earlier this evening, is slowly brightening, by roughly 10% with every billion years that pass. And as it brightens, the gentle warmth that has sustained Earth will, very gradually, become too much. The best modeling suggests that the conditions for complex life on Earth's surface will likely become untenable in something like 1 to 1.5 billion years from now, as the strengthening sun pushes our world past the comfortable edge. Further out still, on the order of a few billion years, the oceans themselves would be lost, much as Venus lost its own. And in roughly 5 billion years, the sun will swell into a red giant, and the inner solar system will be transformed beyond recognition. I want to set those numbers down softly, and then step back from them, because the only honest way to hold them is at arm's length. These are spans of time so vast that they have no bearing whatsoever on you, or on me, or on anyone who will ever live, or on any decision any human being will ever make. 1 billion years is not a deadline. It is not a warning. The complex life of Earth has, by these estimates, something like 1 billion years of comfortable surface habitability still ahead of it, and 1 billion years is longer than complex animals have existed on this planet so far. We are not near the end of anything that matters on any human scale. This is not a doomsday. It is simply the natural arc of a world's long life, seen whole, the way we have seen the arcs of Mars and Venus, and there is nothing in it that asks for fear. What it does tell us, when we set it beside our neighbors, is where we stand in the sequence, and the answer is lovely. Mars is our after. It is what a world looks like once its season has fully closed, cold and dry and quiet, the lakes long frozen, the air long gone. Venus is our after that, or perhaps our other after, a world whose warmth ran past the edge and boiled its oceans into the sky. Both of them are previews, in their different ways, of what awaits any world once its window shuts. But Earth, tonight, is none of those things. Earth is the during. We are not looking at the end of our story, and we are not waiting at the beginning of it. We are living squarely in the warm middle of it, in the long, generous heart of our planet's habitable season, with billions of years behind and a billion or more still ahead. There is an image that holds this perfectly, and it is the one to carry with you as we begin to come home. Think of a long summer evening, the kind that seems to last forever when you are inside it. The sun is low and golden, the light soft and warm across everything it touches. It is not noon with its harsh overhead glare, and it is not yet night. It is that long golden hour when the day has done its work and the dark has not yet come, when the air is mild and the light is kind, and there is still plenty of evening left to enjoy. That is where Earth is right now. We are in the long, warm evening of our world, past the bright noon of its formation, far from the night that will eventually come, resting in the golden middle of the day. And that golden light is exactly what we have been celebrating all along, without quite naming it. Every one of the conditions we have marveled at tonight, the steady yellow sun that does not flare, the magnetic shield still turning in our core, the atmosphere still wrapped around us, the water still pooled on the surface, the chemistry still in its living disequilibrium. All of it is the warmth of this particular evening, this particular stage of the season. None of it was guaranteed. None of it is permanent. Mars had its version and lost it. Venus had its version and lost it. We have ours now, in full, and it is not a small thing to be the world whose evening is happening right at the moment when there is finally someone here to notice the light, because that is perhaps the most remarkable coincidence of all, gentler than any we have touched. Of all the billions of years of Earth's long season, we, conscious and curious and able to look up and wonder, have arrived during the part of it warm enough and stable enough and rich enough to have produced us in the first place. We are not just living in the middle of the evening. We are the part of the evening that woke up and looked around. The same long, golden stability that let complex life arise is the stability we are now using to understand the seasons of other worlds, to read the ghost of Venus and the lake beds of Mars and the flickering of distant stars. We are the universe noticing its own warm evening from inside the warmth. So when we ask where Earth stands in the great sequence of finished and waiting worlds, this is the answer, and it asks nothing of us but to rest in it. We are not the dead world and not the unborn one. We are the living one, in its long, bright middle, holding the season fully open, on an ordinary evening under a steady star. And the most fitting thing we can do with that knowledge, as the night draws in around us, is simply to notice it, to listen for a moment to the sound of a world that is still, right now, unmistakably alive, which is exactly where we will let this long journey come to rest. We began tonight with a question as old as anyone who ever looked up, and a small sealed tube resting in the wind of another world. And now, having travelled all the way out to the edge of seeing and all the way back, we can answer that question gently, in a single quiet breath. The universe may be full of dead worlds, and the reason is not frightening at all. It is only that being a world where life can live is a passing season, and the seasons rarely line up. Let us gather that answer one last time, softly, the way you might fold a letter before setting it down. We watched a small world like Mars cool from within, its inner fire banking down, its magnetic shield slipping away, its air bleeding slowly into space until the lakes froze and the season closed. We watched a near twin like Venus warm past its edge, its oceans rising into the sky and breaking apart in the sunlight, the light water lost forever, and only the heavy ghost of it left hanging in the air. We watch the very zone of safety drift outward as a star brightens, so that a world can do everything right and simply be left behind as the music slides up the keyboard. We watch the most common stars in the galaxy flicker and flare, unable to offer the long, even calm that life seems to need. And we watched, even here, on the one world we know held life, the thread narrow nearly to nothing, again and again. Once, when life itself filled the air with a gas that poisoned almost everything alive. So many different doors, and all of them opening onto the same quiet room. Cores cool, atmospheres escape, stars brighten and flare, oceans boil or freeze, and sometimes life tips its own balance. No single villain runs through all of it. No catastrophe waiting to claim every world. Just the soft and almost gentle truth we have circled all evening, that habitability is a season, that it opens and holds for a while and closes, and that the windows are scattered so thinly across so much time that they rarely meet. That is the why. That is the whole of it. Not a verdict, not a doom, just the shape of how warmth and water and life move through a vast and ancient cosmos, taking turns, passing the light along. And here is the part that turns it from a sad thing into a peaceful one. Tonight, the window is open, not closed in the deep past like the window of Mars, not boiled away like the window of Venus. Open, right now. Around you, in every direction, is a world still squarely in its long, warm evening, still holding its season fully and freely, with someone here, awake, to notice. So let us come all the way home now, from the 13-billion-year-old light at the edge of the universe, back to the ordinary room around you, because that room is the most extraordinary thing in this entire story. You are resting on the surface of a living planet, not a finished one, not a frozen or a boiled or a flaring one, but a living one, in the middle of its season. And the proof of that is all around you if you simply let yourself listen for it. Listen first to your own breathing, slow and steady, in and out, the soft and constant rhythm that has been with you your whole life. That breath is only possible because of everything we talked about tonight, because cyanobacteria once filled the air with oxygen across 1 billion patient years, because a magnetic shield still holds our atmosphere in place, because our steady star has not flared us bare, because the season is open. Every breath you take is the sound of a living planet, drawn quietly through you in the dark. Listen past your breath, to the small sounds of the world holding you. Perhaps there is wind outside, moving through trees that are themselves breathing out the oxygen you are breathing in. Perhaps there is rain against the window, water that has cycled through this planet's oceans and skies for billions of years, falling tonight, just as it fell on the first shallow seas. Perhaps there is only the soft electric hum of the room, the quiet of a warm and settled place. Whatever you hear, it is the ambient sound of a world that is still, unmistakably, alive. Mars is silent now. Venus roars only with heat and acid and pressure. But here there is wind and rain and breath and the gentle, ordinary hum of an evening that has not ended. Both things are true, and you can hold them together as you drift. The window will not stay open forever. No window does. Across spans of time too vast to fear, this season too will slowly close, the way every season we looked at tonight has closed, or one day will. And the window is open now. It is open tonight. It is open in this very room, around your slow breathing, under your settled weight, in the soft sounds at the edge of hearing. The closing belongs to a future so distant it cannot touch you. The openness belongs to right now, and right now is where you are. So there is nothing left to do tonight but rest inside the open window. You do not have to remember the names of the worlds, or the numbers, or the distances. Let them drift away, like the old light they came from. Let your breathing slow a little more. Feel the living planet beneath you, turning quietly through its long, warm evening, carrying you gently through the dark as it has carried every living thing that ever rested upon it. The universe is full of finished worlds, and finished worlds are not a sorrow. They are an archive of long evenings, each one beautiful in its season. And tonight, in this one, the light is still golden, the air is still soft, and you are here to feel it. The window is open. Breathe slowly. You are home, on a living world, in the middle of its long and gentle evening, and that is enough. That was our long, quiet journey through a universe full of finished worlds, and the gentlest idea we found along the way, that a world being alive is a passing season, and that ours tonight is still open. Mars is our after. Venus is our after that. Earth is our warm and golden during, and you have spent this evening resting inside it. Thank you for letting Cosmic Drift keep you company tonight, and for choosing to drift off under these particular stars. It is a quiet privilege to be the voice in the room as you let the day go and the dark settle in. If these slow walks through the cosmos bring you some comfort, you are always welcome to stay with us and to follow along, so the next one can find you on the next quiet evening when you need somewhere soft to rest your mind. There is never any rush, and nothing here will ever raise its voice. For now, though, there is nothing left to do, and nowhere left to go. Let your breathing slow. Let the names and the numbers drift away like old light. The window is open, the evening is long, and you are home on a living world that will keep turning gently through the dark, all the way until morning. Sleep well. We will be here whenever you drift back.